Hello, welcome back. So we ended last time's discussion with the class array list, which we've actually spent quite a lot of time on. In the next portion of the lecture, we'll discuss the linked list, which we've spent 0 time on. So you can learn something brand new. So again, the array list down here inherits from list, which in turn inherits from collection. So the array list has characteristics of both list and a collection. The linked list has a lot of commonality with the array list, and I hope you see that commonality from starting to read this class hierarchy, right? So the linked list inherits from list just the same as array list does, and then indirectly inherited from collection. So the familiar methods from the array list will also be seen in the linked list. And we know that again from looking at the interfaces that it inherits from. It also adds the queue interface, which again is the Java notion of essentially processing data in some type of order. So the linked list is like the array list. It's an implementation of the collection and list interfaces, the collection being the container of object and the list being the order of objects by the notion of the ordering of the objects by index. Unlike array list, it adds the implementation of the queue interface, which has something to do with processing order. Internally, it holds data as links in a chain. So start to think about the linked list as links of a chain and the array list as a block of data. It can get dynamically grow and shrink as needed, just like the array list does. And how do you choose between the two? You choose an array list if you're going to do a lot of insertion and deletion at random locations, and you choose the array list if you are building a stable list. Most of the time, the array list is the correct choice. Not always, though, so you need to know about linked list as well. So, and it does help, I think, to picture it internally. So my first diagram here, I'm going to change my pointer here. Get my laser pointer. So the first diagram here is the array implementation. So inside the array list is this block of data, and think of it as this block of data. Well, think about the actions that happen to that block of data. It's equally fast random access to all the elements here. So this 9th element here is equally easy to get at as the 0 element here. It's a block of data. Or the 10,000th element is as easily gotten to as any of these elements here. It's fast to add elements to the end. It just stuffs it on the end of this list. But it's slow to add elements to the front. Well, think about that. Slow to add elements to the front. If you want to insert a new item here, you have to scoot everything down, and if it's a big list, that's a lot of scooting, a lot of data movement. It's slow to delete elements in a list. Again, a contiguous block. So if you want to delete, let's say, elements 4, 5, and 6, you're cutting those out at deleting them, and then 7 has to move down, 8 and 9 and so forth, down to the 10,000th element. They all have to move down 3 elements in order to maintain that contiguous block of memory. So slow to delete elements. The linked list inverts most of these observations here. So equally fast random elements. So let's look at what the linked list looks like here. Not a contiguous block of memory, but individual nodes that are linked together. So A refers to B. B refers back to A too. This is a doubly linked list, so there's links going in both directions. So you can think of this as a reference pointer to the next, or a reference to the next object, a reference to the next object, a reference to that next object. Think of it as a linked list, as a chain in memory. So it behaves differently. It has different behavioral characteristics. It's not equally fast for random access of all elements because it takes longer to get to D than it does to A. If A is at the beginning of the list, it simply pops to the beginning to A and gets the element A. But if it has to get to the element D, let's say indexed by 3, it has to follow these links down, the order, right? Now, 4 elements, not so bad, but 10,000, 100,000 elements, that means 100,000. If there's 100,000 elements in the linked list collection, that means 100,000 links to follow to get to the 100,000th element. So it does not provide equally fast or random access to all the elements. Since it implements a list, we know it has to support indexes. It's just when it supports those indexes, it has to manually count the elements to get to the index you're asking for, whereas the array just pops right to it. It's also fast to add elements to the end, so this is one thing that's true. Adding a new element to the chain is pretty fast, and it's pretty fast to add elements to the front too. So that is an inversion. So when you're inserting a new element, let's say at the beginning or the middle, you don't have to scoot anything around because you simply just have to change. Let's suppose I want to add an element right here in the middle of this. All I have to do is change these link pointers to point to that new element. I'm not physically moving elements down or up anymore. I'm just changing the link order, right? Think about it physically. Think about you have an order items, let's say books on a bookcase, and that's all in one order, and when you're deleting it, everything has to scoot down, versus links in a chain. You want to add or remove links in the middle of a chain, it's pretty easy. You cut the link, you solder a new link in, and you bind it up. It's not that the whole chain has to move. So the next time we'll discuss this challenge. So the next lecture, part 3, we'll go over this challenge.